Hi, we are Group B16 and today we will be discussing our project on the planar inverted F antennas. With the technology advancements in recent years, the goal has become to make mobile units as small as possible. Due to this requirement, the antennas within the devices have to be adjusted to fit in the units. The planar inverted F antenna consists of a ground plate, a top plate, a feed wire, and a shorting wire attached to the two plates. The PIFA is used for wireless devices where the space is limited. This is due to its compact and adjustable nature. The objective of this project was to design and simulate a variation of the planar inverted F antenna by using openEMS. Our main goal was to design the smallest possible non-capacitive antenna and maximize the wavelength, which would, as a result, minimize the frequency. In order to optimize the antenna, the methodology used was based on parametric simulations. This method allows experimenting with different parameters such as the bandwidth, resonant frequency, the gain, etc. One way to reduce the size of the PIFA is by including a capacitive load. However, after doing our research, we realized that this causes loss in radiation efficiency and bandwidth. This will be further discussed. I'm going to briefly go over what a PIFA actually is. A planar inverted F antenna is a patch antenna, which basically means it can be mounted on a flat surface. It is made of two parts, a metal patch and a ground plate. They usually consist of dielectric substrates in between. The two sheets create a microstrip transmission line. If the length of the transmission line is shorter than half of the wavelength of the frequency being used, then the radiation comes from the edges of the antenna and causes it to act larger than its actual size. In this report, we will discuss the methodology used to come up with our design, the Matlab code, the openEMS simulation, as well as further recommendations of other designs and comparisons to other designs.
Hi, I'm going to talk about our logic of methodology for the PIFA. Here is the PIFA structure. There is a shorting post, a feed line, L1 is the y-axis and L2 is the x-axis. Our goal is to find the smallest non-capacitive PIFA. There are some interesting properties for the PIFA, which is it is symmetric on the x-axis, which means if there's a point on the left part has frequency of 1000 MHz, that means there should be a point on the right part at the symmetric location has the frequency of 1000 MHz. And there are some constraints and freedoms for the PIFA. The constraint is the shorting post, which lock the PIFA at that location. The freedoms are the L1, L2, and the feed line. That means we can change L1, L2, and the feed line. Basically, what we did is just find the smallest resonant frequency on the PIFA. Because of the symmetry, we just need to search for half of the plate. The reason we need to search for the smallest resonant frequency was obvious. We want 2000 MHz resonant frequency for the PIFA. So for example, if the smallest resonant frequency we can find on the PIFA is 1000 MHz, then we can halve the size of both L1 and L2 and it can still give us 2000 MHz resonant frequency. If the smallest resonant frequency we can find on the PIFA is 500 MHz, then we can use the quarter of size of both L1 and L2 and it still gives us 2000 MHz. So the reason we need to find the smallest resonant frequency is to have the smallest size PIFA. Thank you.
Hello. In this section I'll be taking a look at our Matlab/openEMS code, and also we'll be looking at our general results from our simulation. So first of all, what we have here is the simple patch antenna tutorial. It's a Matlab file that's available on the openEMS website, one of their tutorial files, and this is actually the reference code that we took and modified to get our PIFA antenna simulation. So right now I'm going to walk you through this code and let's have a look at it. So first off, we have this physical constants. Unit equals 1e-3, which just signifies that all lengths here are in millimeters. We have a couple variables keeping track of the dimensions of the metal patch for the antenna. In this case, it's a 32 by 40 millimeter patch. Same thing, some more variables keeping track of the substrate this time, and here it's not just the dimension that we care about, but also the material properties of the substrate. The relative permittivity epsilon r, and also kappa, which represents the conductivity of the material. For the feed line here, we have a variable keeping track of the x position and also the resistance, in this case 50 ohms. This vector, simbox, is basically the size of the box in which we're running the simulation. Our simulation box here is 200 by 200 by 150 millimeters in the x, y, and z directions respectively. Now we get to the more interesting parts. Here we're setting up the FDTD parameters, F0 and FC. In this case we're using a Gaussian excitation, so F0 and FC, they basically define the range of frequencies over which we're going to be testing our antenna. So F0 minus FC is the minimum frequency that's going to be tested, and F0 plus FC is the maximum frequency. So here we're going to be testing our antenna from the 1 gigahertz to the 3 gigahertz range. So here when we do FDTD equals init FDTD, we're initializing this variable, FDTD, which stands for finite difference time domain, and that variable we're just going to be using as a data structure to keep all of our appropriate information that's relevant to the electromagnetic simulation. So when we initialize it, we have these two parameters that we pass to the function, nrts, which is a string that stands for number of time steps, and 30,000, that's how many time steps we want. We also pass to FDTD the setGaussExcite function, which lets us know the range of frequencies that we're going to be exciting the antenna with. Lastly, we have this here, 6 strings, which represent the boundary conditions, each one for one of the 6 walls that surround our simulation box. And they're all MUR, which stands for, well, actually I don't know what that stands for, but it represents an absorbing boundary. So when the waves hit the edges of the simulation box, the waves just get absorbed into the walls, and we don't have any reflections or anything like that. And lastly, we pass those boundary conditions into our FDTD data structure as well. Apart from FDTD, we also have CSX, which we initialize here, and that data structure keeps track of all of our CAD geometry for our object. This initialize the mesh, which we'll talk about later, is basically it's 3 vectors, x, y, and z, that we're going to be using to keep track of the resolution of the rectangular cells in our simulation. So for CSX, the first object we create is a patch, the patch for the antenna. So we use this function called addMetal, and this is just saying we want to create a new object with the name of patch. And addMetal says that as a metal, openEMS considers that to be a perfect electric conductor, which is infinite conductivity. And yeah, so first of all we initialize that, and then we have these 2 vectors, start and stop, which both represent points. Start and stop represent opposite points for the rectangle, or for the box of this object. So when we do csx.addBox for the patch, and we pass to it start and stop, that just tells CSX where the dimensions of the object patch are. In this case, we can see that the z coordinate for start and stop are the same, which means that this is a thin rectangular piece of metal. And 10, that's just the priority of the object. Priority is important when you have intersections and overlapping areas. The object with the higher priority is the one that exists in that space. Next is substrate. So CSX, we don't use addMetal here, we use addMaterial because the substrate is not a metal. So addMetal and this string substrate, that's just the name of the object that we're adding to CSX. And because it's not a metal, it's just a material, we need to strictly define what the properties of this material are. So we use setMaterialProperty substrate to let it know that's what we're setting. We give it the permittivity, epsilon r from up above, and the conductivity once again from up above. Those are the variables that were defined at the beginning of this program. Same as above, start and stop represent the edges of this box. In this case it is a 3-dimensional box because the x goes over a distance, the y go over a distance, and the z goes over a distance. So this is a box that rests underneath the patch. And then we use addBox to let CSX know where the substrate exists. And this mesh.z, this just adds some extra resolution through the substrate so we can resolve the electric fields that happen within the substrate with more accuracy. This last rectangular object that we're adding is the ground, so CSX equals add metal, we're calling this GND. We added the start and stop vectors so that it is a flat metal patch that's underneath the substrate, and we use addBox to push the dimensions of GND into CSX. Now, this is the excitation. We have a start and stop vector, and the excitation is a vector going straight up in the z direction through the substrate into the patch, and we use this add lumped port function. A port acts both as a current source, it's the feed line where we're sending the excitation function into the antenna, and the port also acts as a probe. It keeps track of the voltages and the currents that pass through it for every time step. Excuse me. So we can use that as a useful probe to measure the powers that are passing through it and the voltages and all that. Now we finalize the mesh. We use detect edges for the entire CSX object, excluding the patch, because we're going to be dealing with the patch separately. So everything else, this builds a mesh around the object to a certain resolution. And next, like I said, here we have detect edges, and we have set property patch, which basically means this is exclusively looking at the patch. And now that we're exclusively looking at the patch, we have we specified specific resolution that we want, and this is a excuse me, this is a much higher resolution than the standard, because the patch is the part of the antenna that's going to be sending out the radiation, so that's important that we see exactly what's going on there. So we have a relatively high resolution right over the patch, which is the speed of light divided by the maximum frequency that we're going to see, divided by the unit length, and divided by a further 50 for good measure. And we have this function here to smooth out the mesh. And then finally, the entire point of all that mesh work that we've been doing, CSX equals define rectangular grid, and in that function we pass CSX, unit, and mesh. So what this does is it takes the three mesh vectors and it creates a large number of cubic elements in the space around our antenna and within the antenna. And this is all inside the simulation box. So throughout the simulation, openEMS will be calculating the electric field, the magnetic field, the voltage, and the current in each box for each time step. And the mesh just tells what the resolution of these cells are going to be. And pretty much the last thing before we actually start the simulation, this is a calculation box, near field to far field, that's NF2FF calculation box, and this is going to be near the boundary conditions, and this is going to be used to determine what the radiation pattern looks like. This is just setting up the directory inside your computer for where it's going to store the data. This function takes all the FDTD data that was up above and all the CSX data that was up above, and it creates XML files that store all that data in the directories that were just created on the previous few lines of code. This function here pops up a new window that shows the user the structure that's been defined, the CSX structure, and then the user can verify that is in fact the structure that they were intending to simulate. And after the user gives the all green, run openEMS. This is where all the magic happens. We'll be running for maybe 5 to 15 minutes depending on the complexity of the structure that you're trying to simulate. And after that's done, all the data is dumped inside the directory, and then we can use processing on that data to get useful information out of it, which is what happens in this calc port function call. So after that's done, all the useful data exists as vectors of this port variable. So you can have here port, you can see this is the total voltage, the total current, the reflected voltage, the incoming voltage, and all that useful information. Like I said from before, the port also acts as a probe from which you can get all the useful data. Here are a few calculations. For Zin, it takes the total voltage divided by the total current. For the S11 coefficient, it takes the reflected voltage, which is the voltage that goes backwards through the port, divided by the incoming voltage, that's the voltage going to the antenna from the port. And also there's the power calculation here. Now that you have all that data, all you need to do is do the plots that you need to see. So here's a feed point impedance plot. There's a reflection coefficient plot, which we use a lot in our PIFA simulations. And also we have radiation pattern plots, both in 2D and 3D, that use the near field to far field variable that was defined just up above. Alright, so now that we see the basics of the simple patch antenna tutorial, let's take a look at our PIFA implementation. So we've just made a few simple edits to the patch antenna tutorial to get our PIFA. So apart from just what you might expect, changing a few dimensions here and there, we also have this new variable, short, which represents a new CSX CAD object. So we have a few variables: short width, short Y position, short height, and etc. So apart from that, let's see what else is different. In this area where we were adding all the CSX objects, we have a new section here where to add our shorting post to CSX, we just did following the same style that was up above. CSX equals add metal CSX short, which means the object, or the name of this object, is going to be short. It's a metal perfect electric conductor. We have a start and a stop position that represents that rectangle. This is actually going to be a metal plate that's going to create a short between the patch plane and the ground plane. And then lastly we use add box to push the dimensions of this short object to CSX. Okay, so let's see what else is different. For the finalizing the mesh, we did the same sort of strategy that they did, because this short is a object of interest. So we did exclusively for the short, we want it to look at that with a high resolution. So we did set property short, which means exclusively look at the short and create a mesh around that with a certain resolution. And that's pretty much it. Now, the problem with this code is that to find our optimal structure, we need to parameterize the x and y position of the feed line. And to do that manually, we'd have to physically edit these two variables and then run the code every time, which would result in a lot of excess work. So what we did is we created something of a template here that we passed to each member of the team. So right near the top of this template is these variables: xmin, xmax, ymin, ymax, and step size. And basically what every member of the group had to do was to change these to his or her assigned area that he or she was covering for the PIFA positions for the feed line, x and y positions, and then run it, which would create a number of text files for output, and then everyone could just put their text files together, and then a person could analyze the text files to find the optimal structure. So let's see how this works. Scrolling down here, we have numx is equal to the difference between xmax and xmin divided by step size plus 1. Same thing for numy. This is standard for loop stuff. And then we have this xy mesh grid that goes from xmin, step size, xmax, ymin, step size, ymax. So basically it goes through a double nested for loop, and for every iteration of the for loop, the feed line has a specific x and y position, and after it goes through the entire for loop it goes through the entire two-dimensional for loop, by the end of it, every single x and y position feed line will have been covering the entire area over here. If we were to do this all in a single run, this is the single run here, 15 to 30 x, 1 to 40 y. That's many hundreds of simulations. Each one taking over 10 minutes will take a lot of time, which is why we thought it was a good idea to split it up among the group. Now, let's look at what changes we've made to this code specifically. At the beginning of every iteration, it displays the current progress that's made, so you know whether or not something's stuck or how much longer you might expect the code to run. Apart from that, we have this CSX geomplot. This is the function that popped up the window to show you the structure that you were trying to simulate. The reason this is commented out is because this doesn't actually have any impact on the simulation. This is just to verify that the structure is correct. And with this commented out, the openEMS will just run continuously in the background without any user input required. Apart from that, actually this was in here when we ran the code. So this calcport function, you can also apply filters onto the end of it. In this case, we're using AR auto. AR here stands for auto regressive filter, which basically acts as a low pass filter, because we were noticing that some of our outputs for our plots oscillated as if it was a sine wave, and that was entirely not normal, especially because many of the oscillations, the S11 value in decibels was above 0, which is physically impossible. So we applied this as a filter which smoothed out our plots, and it basically lets us see more accurate results at the cost of a little computation time. Apart from that, we also have this right at the end. So after every simulation, what it does is it plots our S11 plot, and that keeps that open until right before the next one's about to be plotted, in which case it closes the old one, then plots the new one. The reason we did that is that this doesn't require any user input, but it's also very helpful. The user is able to take a look at the most recent S11 plot to see if the code's running as expected or there's something incredibly wrong with it. At the end of every simulation, it has this file name that it generates based on the current X and Y position of the feed line for the simulation that's just been ran. It creates that file name string that specifies exactly what the X and Y position for that simulation was, and it outputs the S11, the reflection coefficient vector, into a text file. And after this run, many hundreds of text files exist, but it's very easy to sort through them. In fact, if you look to our left here in the folder, I do have many hundreds of text files here, and each one contains semicolon delimited data, which represents the S11 vector, and then you can easily look through that data to see where which of your antennas perform well and which of them do not perform so well. Okay, so now you might ask, how do we analyze all this enormous amount of raw data? We're not about to do it manually, because if we open one of these, yep, look at that. We just have a large quantity of numbers. So we're going to have to do this either through code or visually. I decided to do it visually because writing the code to analyze that seemed like it took a bit too much time, and it wouldn't save me much time in the long run. So I have this function here called plotter, and essentially what this does, it's the same sort of interface up top. You set an xmin, xmax, ymin, ymax to cover a certain area for possible feed line positions, and also a step size. And what this does is it searches for the corresponding text files that were created, and for each text file it creates a plot for the reflection coefficient. Here I already put in x goes from 24 to 26, y goes from 1 to 39, step size of 2 for each one, and if I click run here, it'll read through the appropriate text files and it'll bring up a plot for each one. So let's see what happens. Okay, there you go, 40 figures brought up just like that. Also, I changed it so that in the title it says where the X and Y position is, so that it's a lot easier to see what happens. So, right away, searching through a few of these, what do we see? Okay, we're starting to see a trend. Most of the structures have a resonant frequency of just about 3,000 or 2,700 around megahertz, and also there's a bit of a dip around the 1,000 megahertz range. And if we close through these, we'll see that that's a general trend. 3000 or 3 gigahertz is the main resonant frequency for this type of a structure, but there's always something, or there's almost always something of a dip around 2700 and also around 1 gigahertz. If we look through enough of these, here we're starting to see that for certain implementations, the reflectivity at 1 gigahertz gets fairly low, almost low enough for this to be considered viable as a 1 gigahertz antenna. So we just search for the ones that have really good performance around 1 gigahertz. Although we've noticed that this is something of an anomaly, seeing that 3 gigahertz is the standard resonant frequency for this dimension of an antenna. But sometimes where we can find very good performance around 1 gigahertz, the trade-off is, if we look at the bandwidth here, it's very tiny. So it would be very difficult to implement this in real life unless you had a very precise signal generator that kept the frequency within a very small bandwidth. But within that bandwidth, it's possible to get some decently well-performing antennas. So what we did is, here, I created an Excel file, and I manually went through all the different plots from all the text files, and I put in what the performance at around 1 gigahertz is. Because now that we've noticed that a lot of the resonant frequencies tend to clump up in the areas of 3 gigahertz, 2.7 gigahertz, and 1 gigahertz, we can just look at the 1 gigahertz specifically and pick out the ones that perform decently well at 1 gigahertz. So if you look at the trend, near the back of the antenna, anything upwards of 10 millimeters to 40 millimeters, none of these perform very well at 1 gigahertz. All of these perform very well at 3 gigahertz, but that's not what we're interested in. For whatever reason, what we're interested in, or what we should be interested in, is where the feed line is within the first 10 or so millimeters from the shorting post. And that's where the 1 gigahertz performance of these antennas is very decent. So what I did is I manually went through all these, and then we ended up picking the one that performed the very best, and that is the antenna template that we chose to scale down. So going back here, once again, I just ran a verification for that specific structure where the feed line is x is 16, y equals to 4, to see what that output looks like, and it ended up looking good for the verification. So then we just shrunk that down by a factor of 2 and ran that, and that was our final structure. That was our miniaturized PIFA antenna that operates at 2 gigahertz and has good performance at 2 gigahertz.
Now I am going to discuss the actual results we achieved by running our Matlab simulations of the PIFA using the openEMS plugin for Matlab. After running the simulation with a patch width of 30 mm and a patch length of 40 mm, we were able to determine the optimal feed pin position. The position was 80% towards the edge along the patch's length and 6.7% towards the edge along the patch's width. Shrinking the PIFA down, we were able to obtain a patch width of 15 mm and a length of 20 mm. Given these dimensions, the feed pin position is 0.5 mm in the X and negative 8 mm in the Y, where 0, 0 is the center of the PIFA. The resistance of the feed pin in these simulations was 50 ohms. For the simulations, we had the shorting pin to be the entire width of the PIFA, as it had been determined in previously published work that this is the optimal dimension. In our project, we had decided to focus on optimizing the feed pin position. The relative permittivity of the dielectric used in these simulations was 3.38, and the conductivity was 4.6 times 10 to the minus 4. The dielectric had a thickness of 0.762 mm. The final performance of the PIFA we designed had a resonant frequency of 2.019 GHz, and this frequency produced an approximate S11 value of minus 5.2. Here is a plot of the S11 values versus the frequency. The bandwidth here represents the range of frequencies which provides a reflection constant below 0.63. Keep in mind that this graph shows the S11 values in decibels and that the reflection constant is related to the S11 value by the equation shown here. That is, the S11 value equals 20 multiplied by the log base 10 of the reflection constant. The reflection constant squared represents the input power loss as a percentage. The power loss within the bandwidth shown here is below 40%, and at the resonant frequency, the power loss is approximately 28%. This means that the antenna is approximately 72% efficient at the resonant frequency. This is the 3D plot of our electrical far field radiation from the PIFA. It represents the strength of the signal at far distances from the antenna. You can see the antenna radiates stronger in one direction. This is due to the way the field lines add up in one direction and not in the other two. This output is not ideal, but it is okay in practice as the field is not too weak in any one direction. In fact, it is impossible to achieve a perfectly spherical radiation pattern in practice.
And now I'd like to talk about further simulations that would help us determine an optimal PIFA antenna design. In our simulations, we focused on the position of the feed point and kept all other variables constant. In total, the simulations experimenting with this one variable took around 56 hours to complete. With more time or more powerful computers, we could also look at the effects of other variables. This includes the height, width, and length of our antenna. In addition, our simulation used a shorting post that had a length of the entire width of our patch. Different variations of the size of the shorting post and its position would help us determine its effects on the resonance frequency. We could also try the use of a shorting pin instead of a shorting post. Lastly, we could look at the effects of using different materials to make our PIFA antenna. Our project focused on a non-capacitive PIFA antenna. If we were to further our simulations, we could use capacitive loading on our antenna. The introduction of a capacitor would bring forward more variables to consider. This includes the value of the capacitance and the position of the capacitor. Although the capacitor would reduce radiation efficiency and decrease bandwidth, it would also decrease the size of the antenna. Therefore, this compromise would depend on the preferences of the user that the antenna is designed for.
I will now talk about the comparison of our results to other published works. We found that most of the published research relating to the wireless cellular use of the PIFA used the multiband PIFA, which had a much more complicated radiating path that allowed for multiple resonant frequencies to be achieved, in comparison to our single band PIFA, which allowed only one resonant frequency to be achieved. One of the most similar works that we found was done by a group of 3 people, including Abdul Hakim Aluadi, Ahmad Ulad Said, and Moha Hassani of the Department of Electrical and Telecommunications Engineering at the Royal Air Academy in Marrakesh, Morocco. In their work, they described the design and simulation of a single-band PIFA for the use in a personal communication service band with a frequency of 1850 MHz to 1990 MHz. To simulate their work, they used a high-frequency simulator structure. Through their testing and simulation, they were able to gain values of different parameters, including ground plane widths and lengths, shorting plate positions and widths, and as well as feeding point positions. In this table seen below, the comparisons of their values can be seen with ours. When comparing our output reflection coefficient, we see that ERA decided to run the test between 0 GHz and 3 GHz. They found that their simulation peaked at 1924 MHz, close to their desired 1920 MHz frequency. For all other values, the value is 0, meaning that nothing was radiated at other frequencies. We decided to run our test between 1 GHz and 4 GHz and saw a peak at 2020 MHz, which is close to our desired 2000 MHz frequency. Similar to ERA simulation, we managed to obtain values of 0 on all other frequencies. This shows that both our antennas respect the requirements for such a reflection loss with the high radiation efficiency of a single-band PIFA. ERA found that their maximum electric field plane was at a maximum when phi equals 0 degrees and theta equal to 56 degrees. Our results showed similar behavior when we decided to test for phi at 0 degrees and phi at 90 degrees. This is further verified by the 3D simulation of the polar electric field diagrams. These diagrams can be seen in figure 3.1 and 3.2. Both our and ERA's polar diagrams show a strong electric field at the edges and a weak field in the center. ERA's electric field seems to have been stronger and more consistent than the one that we simulated. Another group of people whose research we compared our work to is the research of Abhay Sharma, R.P.S. Gangwar, and Shakti S. Chauhan of the Electronics and Communication Department at the College of Technology in Patnagar, India. In their research, they designed and simulated a multiband PIFA that they found suitable for a modern mobile application. To simulate, they used spatial network method and ZLAND IE3D. Similar to ERA's work, they simulated to find the optimal ground plane width and length, height of the patch, and different antenna locations. The values that they obtained can be seen in comparison with our values that were obtained in the table below. As previously stated, the College of Technology decided to simulate their research on a multiband PIFA, whose schematic can be seen as a little bit more complicated than the one that our group used for our simulation. When comparing our output reflection coefficient, the College of Technology's team decided to run a test between 1 GHz and 6 GHz, and they found multiple resonant frequencies, which occurred at 2,199 MHz, 3,721 MHz, and 5,180 MHz. Ours, however, only dipped at 2,020 MHz. This showed that their multiband was able to cover multiple frequencies such as UMTS, LTE, MYMAX, and WLAN, while ours only covered our single desired band of 2 GHz. In both our simulations of the resonant frequencies at around 2 GHz, it can be seen that the electric field is omnidirectional, which is suitable for mobile phones. Comparing our simulations, it is clear that the College of Technology simulation seems to have a consistent drop in field intensity as you approach the center, whereas our simulation seems to have a strong field at the edges, but the field drops very quickly as you approach the center of the simulation.